less invaded. Okay, as we have done it in the first major test. Okay.
Yes, sir.
So it means we don't have a problem MTech design guys, because our lectures are till 1 p.m. only on Monday.
But we have a large number of dual degree students.
Yes, sir.
And there will be Viva, I think MTech first year and dual degree. The comprehensive Viva will be scheduled, I think, between 15th of April to 22nd of April, something like that. So it will be better if we actually do the test on 12th, Monday. Okay, so you are free from the course and you have also the full comprehensive idea about this subject. And then you can concentrate on the comprehensive Viva. So MTech first year students and dual degree students, they have to appear for the comprehensive Viva between 15th of April to 22nd of April. Okay? Are you hearing? Because I am the postgraduate coordinator for all the sections, ME1, ME2 and ME3. And we had a recent meeting with the section coordinator and myself, the head of the department. So basically, we have fixed up the schedule of the comprehensive Viva. Also, there are MTP, I mean the MTech thesis project Viva. But that is not your concern, because you are now MTech first year or dual degree, not the final year students, right? So comprehensive Viva of MTech first year and dual degree students will be held between 15th of April and 22nd of April, because we have to do it in parts. We have to do it either on telephone or there will be several boards, maybe one-man board, something like that. But there is a lot of students, and we need about a week to complete that. I think 84 is precisely the number, somewhere around 80. But as per the academic calendar, all the courses should be completed with tests, everything should be completed by 14th of April. Okay. So that's the reason I want to keep it on Monday evening, say 6:30, something between 6:30 and 7 p.m. The major test 2, right? So I take it for granted, and then I will make that announcement, put it in the post well in advance. Okay? Hello?
Okay, sir.
Because I want to complete the course precisely within the first week of April.
Today's video is about Hashing failure criteria implementation in
By
Abnormalities.
7th or 8th
Hello,
of
everybody.
April, in that week, 9th of April, maximum 9th of April. 9th is a Friday. So by 9th of April, all things will be complete. On 12th, you appear for the major test. Okay?
So will this test be of the same mode like the previous test?
Yeah, somewhat.
That means both MCQ as well as subjective will be there.
So let us see. We have not completely decided, but definitely MCQ.
Good morning, everybody. So, considering the situation in our campus, we will now.
So you have to read things very precisely, materials, because if it is an MCQ test with multiple answer correct, then you have to be precise in your answers. Okay? Okay. So I understood I will put that in the post well in advance. But what I am sort of thinking is that I would like to end the course during this time. We will complete the rest of the thing. Only the tissue engineering part will be left. We will complete it within a week. So that would be in April. Okay? The last topic. We may start end of March. The 31st there is a class. 31st, 1st and 2nd. And then, if necessary, 7, 8, 9. Okay. Now, before I start the class, I would first like to show you let's see. Yeah, this is basically, I think you people have seen, this is precisely the knee joint. Okay? So what you see is from the front, the natural knee joint. This is from the side. This is from the back. You can see the cruciate muscle. Also the collateral muscles. Also another view from the side. So this is a right knee joint, okay? Because the fibula is located laterally, right? We look from the front, the patella is here. Now what I will show you is, just a moment. Is the still not. Can you see it clearly? Hello?
Yes, sir.
Yes, sir.
So this is a model of a knee replacement. So if I keep it maybe side by side, it's difficult. You can see the difference. Okay? Right?
Yes, sir.
Now I will actually open up this whole reconstructed joint. You can see how it rotates.
Yes, sir.
And I should show you also the back part. So when you operate, after you do the replacement, you can actually restore back all the ligaments and muscles back in position, except something, depending on the design. You can see here that there is no place for cruciate ligament. Okay, so this is cruciate sacrificing, the SCL and PCL sacrificing design. So there is, if you look from the front also, you can see that there is a, here, there is, it is, the design is such that the stabilization or the stabilizing function of the cruciate ligaments are not necessary anymore. It cannot actually tilt too much on the both sides. Okay, it will be held in position by the collateral ligaments and other ligaments, but cruciate ligaments is not anymore necessary. Okay. Okay. So what I will do now is open up this joint. So let us first consider the tibial part. Can you see that? But I need to put it up again. Let's see. Put this up. Now I think the height is okay. Isn't it? So this is the implant. Right? It has two parts. One is the tibial tray with a pillar that goes inside the resected part of the tibia, and there is this, you know, from side, from front, from back, you can easily see a polyethylene component. Okay, so depending on the design of this polyethylene component, it will be either cruciate sacrificing or cruciate retaining type of knee replacement. Now this can be actually cemented or uncemented. So we use cemented fixation generally for, you know, patients who have poor bone quality. Okay, so you need to fix the implant with the bone, and traditionally bone cement was quite popular as the fixing material. As I told you, bone cement is polymethyl methacrylate. So I will talk about those materials, different implant materials, and this sort of cement separately in a brief lecture. But obviously, before you actually put in cement, you can see that how this bone is resected. Okay, so if you are comparing with the natural knee, you see that absolutely the articulating zone of the tibia is cut off completely to make way for a very nice surface for the implant to be seated. Yeah. Okay, and of course you have to drill holes to accommodate this fixation implant. So there is a lot of machining involved before you actually insert the implant in position. Okay. So now when you have prepared the bone for implantation, bone cement mantle is prepared by mixing powder with a monomer, and then it becomes a semi-solid, something like a dough. and then you insert it. It is vacuum mixed and it is inserted, and a proper thickness is maintained according to the surgical guide, and any excess cement is cleaned off, and immediately, because cement starts solidifying within 10 to 15 minutes. So you have to be quick in putting this implant within that, and with jigs and fixtures, you hold the whole thing in position, okay, and let the cement solidify and fix the implant. So this is the basic type, okay. Similar things are done for the other part. Let me just take it out. So this is the femoral side, the distal part of the femur. Okay, so you can have actually so this is the sort of machining that needs to be done, the preparation, bone preparation, before it can be ready for implantation. Okay, so you can see here also the two condyles, medial and the lateral condyles of the distal part of the femur, are actually prepared to accommodate this implant. Okay, this is the femoral implant. Now together, it actually gives you the required or desired motion. Now, as you can see, just a moment, this has come up from somewhere. Where it has come up. This is basically the model of DePuy Johnson & Johnson, that model, very famous, PFC Sigma, okay. Our former Prime Minister Vajpayee was operated with this implant, okay. So this is where I worked as well, DePuy Johnson & Johnson. It's a very famous implant, and there was eminent Indian origin doctor C.S. Ranawat, Chittaranjan Ranawat, who was actually involved from the clinical side regarding the design of this implant, knee implant system. Okay. So nowadays there have been different variants of the knee implants. The first variety is the fixation. The difference in fixation. People use also, a lot of interest is now shown towards the biological fixation. So uncemented implants are getting more and more popular. The tissue ingrowth, bone ingrowth, facilitating porous coated implants. And you can also have partial, you see there are two condyles here. Okay, one is, if you also want to see this side by side. So this is the medial side, this is the lateral condyle. So if the surgeon decides that it is sufficient to operate on a single condyle, okay, so we can actually have a knee replacement done on only one plateau. Okay, it may be a medial plateau, it may be a lateral plateau, depending on the extent of damage or bone degeneration. Okay, so this sort of partial replacement is also done specifically on, depending on the degree of bone degeneration of the system. Okay, so in that case, only half of the knee joint will be operated, and accordingly the implant will be fixed to save. So once you save, once you actually operate and put things, you open up and you clean it and then you put things back to restore the movements, then a patient comes back to normal life, and more the mechanics is restored to a great extent. Because earlier what happened is that there would be disturbance or deviation from the normal structure. So the legs may have, the knee joint may have bended, so one side is loaded more, one side is less loaded. So one plateau is predominantly more loaded, giving rise to more bone damage and more pain. So once you restore the joint to a reasonably normal position and orientation, it is far better for the patient to come back to normal gait and normal forces and the articulation, so as to save the other portions of the body. Okay, so in many cases, it has been seen that one knee joint, say left leg or right leg, is severely affected, and if the other knee joint is saved primarily because the severely affected joint is operated on time. Okay, so once you operate on a severely affected knee, one knee, then the other knee is saved because the whole thing is restored back to normal. Okay. The moment you have pain in one of your leg, you will tend to load the other knee to a greater extent. You get my point? Okay, so even if there was, abnormalities in the other knee, but to a lesser degree as compared to the other knee joint, but that is rectified because the other more severely affected knee joint has been, taken care of by this reconstructive surgery in time. Okay.
Sir?
So please.
So usually pain occurs in the joints because of the sensory nerve that connects the bone, that connects to these joints. And what happens to those nerves post-operation? I mean, they are not connected at all, or
no, this part, see this part, when you actually operate, you have seen that these chunks of bone are taken off. Okay, so there is no, the top part is not there.
Yes, sir.
The pain, so see, pain is a manifestation, right? Pain is a manifestation, but if you look at osteoarthritic patient, I have shown you some slides initially, I think. The knee joint severely affected. Didn't I?
Yes, sir. Yes.
Yeah. Say X-ray. But if you just visit the website and ask for osteoarthritic knee osteoarthritis, you'll get loads of digital X-ray or CT scans actually explaining you the abnormalities. Okay. Structural abnormalities. Basically a structural abnormality because the cartilage is worn away. And the bone, a subchondral bone below the cartilage is exposed. And, you know, this sort of, if I look into a normal knee, so it will be tilted on one side, either this side or that side. So the joint space is reduced on one side. So, and the cartilage will be no longer very smooth. It will take a spiky pattern. I think I have explained you in the first lecture. Okay, if you
Yes,
go back to it. And it will have a spiky pattern, and with more and more use, the cartilage would be worn away, giving rise to more severe problems of pure bone to bone contact. And you know, that time already the pain has set in. The pain will be abnormally high and it will be very difficult for a patient to carry out normal life, okay, normal activities. So he or she almost becomes immobile because a patient cannot sustain pain of bone to bone coming in contact. And remember, there is a huge amount of load that is transferred through this knee joints or hip joints or any other load-bearing joints like shoulder. But of course, shoulder is lessly loaded. But the whole body weight is actually being transferred through the hip to the knee and onto the ankle.
And so, what is the usual life of these implants? I mean, are they lifetime? Because 2 years back, I think,
Good question.
Johnson and Johnson company, I think they paid around $2.5 billion to the US citizens because they had some faulty implants.
Faulty implants, you know? Which implant?
Sir, hip joint, sir. So
Yes,
that joint.
That is what I had explained you. We had a series of paper, the resurfacing implant.
Yes, sir.
Resurfacing implant. Okay, that I have explained you. Okay, they have taken out. They had to. Generally, the life expectancy of these implants are about 20 years, almost a lifetime. Okay, but there may be cases when, say, this polyethylene component is worn away to some extent. You can actually monitor that, right? My mother was operated in July 2003. So how many years now? Almost 18 years. Yeah, she's doing fine. And she was operated with PFC sigma in Delhi. Absolutely no problem. I have a patient at home and I could monitor her proceedings in front of my eyes. And the feedback is, I feel my operated knee is better than the normal knee. I can rely on that more. This is basically the feeling. I have problems in my other knee. She's 86 years old, but she complains of pain sometimes in the other natural knee, but she never complains about anything in the operated knee. Okay, it is a grossly successful surgical procedure Of course, it's a surgical procedure, but there is a huge contribution from scientists, engineers in restoring or challenging the gift of God. Okay?
Yes, sir.
Well, that time when I actually decided to go for a knee replacement for my mother, it was not at all a very popular surgery in India. I think you were all kids that time, 2003, July. And I was leaving for the fellowship in England. And before that, I wanted to carry on the surgery because I was on a big fellowship, 1+3 years. And I was not certain that I might not return to the country permanently. Okay. So I had to do some of my duties towards offering this solution to my mother. And I made sure that before I left in August, this surgery is done. And you know, it was difficult to find surgeons. It has just set in. You know, the trends few people. There was a doctor called P.K. Banerjee in Peerless Hospital in Calcutta who had this experience of doing knee replacement. Because here, you see, the experience of the surgeon is extremely important. He needs to excel in surgical technique, and he has to really work like an engineer, measuring all the angles, you know, the prescribed surgical procedure. This surgical procedure involves a lot of measurement. So he has to work like an engineer, but deal with a complex biological system. And that time when it was in Delhi, in probably Apollo Hospital in Delhi, was Dr. S.K.S. Maria. I came in contact with him, and the surgery was carried out to take my mother to Delhi. And it was done, you know, he also worked in Southampton and Winchester. And he was in NHS. So they were experienced, qualified doctors who can handle such systems. So I had to rely on him. He did a great job. And this last year we took a digital X-ray just to follow up what is the state of affairs. I had a chat with one of my very good friend who is now in Fortis Hospital in Calcutta, and he said, "This is now it is almost, you know, I know at least one of my doctor friend who is eminent orthopedic surgeon in Calcutta. He does 3 knee replacements per day. So 3 into 365 is the yearly. Minimum 3 is the schedule. Okay. Now, during that time, 2000-2010, that whole decade, the WHO dedicated the world population regarding bone degenerative diseases. So that was a time when many things were developed all over the world. And particularly, you have seen what you were saying, Shivangshu, that DP Johnson & Johnson had to pay a huge amount as fine because of a wrongly designed implant. Okay. Now this actually, I was involved in the genesis of finding out the fault, but it is a very promising implant. But there were few things that need to be fixed because, you know, these things, you know, it comes as a feedback from the clinical world after surgery. So as I shown you in that Shimin et al. Paper, 2008, Journal of Bone and Joint Surgery, that how this failure of the implant, of the resurfacing implant, that mushroom type implant, was initiated from the superior part of the neck, and then in no time it propagates through, it cracks through the neck of the femur. Okay. So these are, you know, it was very early failure. Rather than any other factor. Because the moment you load the implant, it starts developing problem. Okay. So there are many issues. Things are still evolving. You know, new implants, new concepts are coming, and I have been working in this field for about more than 25 years, and you know, the problems are, you know, quite clear now, that it is very difficult to replace bone. Okay. Let us be very honest in this field. Bone is such a material that it is very difficult to replace the function of bone by putting an implant. Okay, so one has to be very careful in designing an implant that it serves the purpose it is selected for. Okay, earlier it was conceived in a way that if there is problem, cut off the bone, put some cement, put some implant in it, and then everything will work. That is not anymore the idea. Okay, the idea is more try to preserve as much bone as possible and insert the implant so that you have minimally invasive surgery so that the motions are done. Now, you can, from a patient's point of view, you would like to get back your normal life, normal movements. But that is not possible because on the articulating zone, the cartilage and the bone is degenerated. So what happens is that we are more concentrating on the articulating zone rather than removing a huge chunk of bone from the bone structure. You get my point?
Yes, sir.
Now, one thing also I would like to say that you can see that this is a reconstructed joint and you keep on using it. And there will be a lot of wear between articulating bearing surfaces, technically speaking, bearing surfaces. Now that is another huge area of research, biotribology in this area. Okay. Because earlier it was conceived metal on plastic or metal on polyethylene was a solution. But actually, it has been observed over years that the metal on polyethylene bearing surface generates a lot of wear particle debris. And these wear particle debris are actually highly active and they react with bone cells. Now then came metal on metal bearing surface to reduce wear. But that also gave rise to generation of metallic ions that actually reacted with bone and blood cells. Okay? Then came ceramic. Ceramic is a very wear-resistant material. Bialex Delta, so alumina ceramics. It is a highly wear-resistant material. It gives rise to very low volume of wear particle debris, the wear rate. But ceramics has an inherent problem of being brittle in nature. Okay, so a lot of work is still going on in improving ceramic material used for orthopedic application, where it can take some tensile loads as well. Okay. Now, more recent developments are on polymer composites, composite materials. Okay, like as I've shown you, PEEK, polyethyl ether ketone. Okay, CFR PBT. Okay, so you have polybutyl butatetraphthalate, PBT. Okay, and finally, the area where SEBI is working is functionally graded materials. Okay, functionally graded implants, porous implants, not anymore solid implants. Okay, porous implants, functionally graded implants. These are the new generation, implants that people are thinking about, so as to optimize the solution or trade-off between various requirements. Did you get my point?
Yes, sir.
Okay. Now I will give a brief lecture on the shoulder replacement, a few slides, because there I will highlight the how interface failure is assessed. That is used for all other joints, just for an example. And shoulder implants would also be explained. So, thereafter, SEBI has planned another brief lecture, and together we have discussed. We will talk about anisotropy. So, all this while we have been considering bone as an isotropic material, which is basically an assumption. Okay, how good is the assumption? It is definitely not purely an isotropic, as you know, material, because it's a porous material. So as the porosity increases, more and more osteoporotic patients will exhibit orthotropy in bone, because it is becoming more and more porous. Less porous bones obviously have similarities with the assumption of isotropic material, but that is generally what we had assumed. He will talk about the difference between isotropic assumption and anisotropy bone properties separately. Okay, so let me go to the lecture on the shoulder. You have already the slides with you. This is the slide, shoulder biomechanics and replacement. Shoulder biomechanics and replacement extra, as I had called it. Maybe I have just edited a few things here and there. So I'm going to the slideshow mode. Can you see the slides? Hello?
Yes, sir.
Yes, sir. Yes, sir.
So I'm not putting anybody muted there. So I'm carrying on with the lecture in this mode, because I see that the students are matured and they're well behaved now. So please don't try to fiddle with the meeting option. Okay? So I'll keep it in interactive mode, right? So this is the lecture on shoulder biomechanics and shoulder replacement.
Can you please start the recording?
Why do you always need recording? No.
For
Why do you
future
need
reference, sir.
future reference? I will refer to the GAN lecture. Okay. Try to listen when I'm taking the class. Try to listen. Taking part in the class discussion is very important. I'll give you the GAN lecture link where you can go on playing again and again. Okay, so this we have covered earlier. Up to this. So this is all covered, isn't it? Hello?
Yes, sir. Yes.
Yes, sir.
Degrees of freedom, loading conditions. Yeah. Now we come to the implants. So what is the clinical relevance of this? Let us start with a X-ray of a shoulder replacement.
Now
you
it's
see here that
happening.
Yeah, so now you
the glenoid component, the glenoid part has been replaced by a glenoid component, and there is a humeral prosthesis. The humerus, they are articulating. So this is post-operative, less than 1 year. Okay. MB stands for metal backed polyethylene, similar to what I had shown you as the TBL component of the knee prosthesis. Okay, so it has basically two parts. One is a TBL tray, and there is a, on top of it there is a polyethylene component. Okay, so this is a metal to polyethylene bearing surface, right? Now, after 10 years, the same patient is developing the problem of shifting of glenoid component. The glenoid component is more or less mobile. It is shifting. In a purely polyethylene, there may be another type of design which is totally polyethylene, total polyethylene. Okay? You can see, if you watch very carefully in the slide, there is a black line being developed around the keel, the base of the prosthesis. See all around, black line, follow the laser pointer. Okay? Cement bone radiolucencies. Radiolucent lines at the boundary of the cement and bone, interface of cement and bone. This is after 10 years. Okay? Uncemented variety of glenoid components. See, there is this solid peg going inside. There are also screws to hold the prosthesis in place because it is, you need a fixation. Fixation is a problem. There is no cement here in this whole system. Stress shielding and bone loss, bone resorption and stress shielding appearing after 3 years. How much bone has resorbed around this? Okay, so this is resolved, but this is also, there is certain fixation also. So this is normal, you can say, but here it is, there is the prevalence of bone resorption and stress shielding is all through adjacent or around the periphery of the prosthesis. This is 10 years after post-operative on the right, but this is only after 3 years. So the motivation of the study is that clinical and radiographic studies indicate implant loosening, in this case glenoid component loosening. We have a glenoid component, we have a humeral component, and together it makes the shoulder replacement. So we have glenoid component loosening as the most frequently occurring problem in total shoulder arthroplasty. Okay, so this is a shoulder replacement. The precise relationship between the cause and the effect. So we will be investigating the mechanical causes of loosening using a three-dimensional finite element analysis. And of course, this is a study carried out way back during my PhD. So it is quite old, but still very relevant, using the computed tomography scan data. Now, if you look at the loading of the glenoid component, so because it is a highly mobile joint, high degree of movements, you see the contact of the humeral component with the glenoid component actually varies from one location to the other, giving rise to a rocking horse effect. So at one position, it is almost at the tip where you are pressing in. Obviously, the other tip tends to move out. Okay? This is when it is more centrally loaded. But if you move to the other side, and the same thing, similar things happen on the other tip, it tends to move up. So the rocking horse effect of the movement of the humerus on the glenoid component is a real challenge to develop, to design the whole replacement. If you look at the CT, starting with the CT scan slice, this is typically a CT scan slice, where you have the scapula very clearly, the clavicle, the collarbone, and the humerus. So we are interested about scapula. So before analyzing a prosthetic joint, implanted joint, it is first important to evaluate the stress distribution in the natural scapula. So first we get hold of what is happening, the level of stress, quantity, both quantity, quality, distribution, everything in case of a natural. And then what are the deviations and why are these deviations and how can we rectify these deviations to bring it back to a normal situation? That can be done using the implanted joint. So it is important to evaluate the stress distribution in the natural scapula acted upon by all muscles, ligaments, and joint reaction forces. For that, we need to develop a realistic finite element model using CT scan data. For geometry and material properties, as I told you earlier, we employ the layer reconstruction method based on detection of the contour data from CT scan slice, from contour to surface, surface to volume, and then we actually develop a solid model, then a finite element model. We have to do calibration of the pixel gray values in terms of apparent density. From apparent density, we use the power law relationship specifically for the shoulder bone, and we get the elastic modulus. And obviously, we use the concept. There are some data of the glenoid component, glenoid area of bone, which can be fitted to the theory of open cell structure and closed cell structure. So here also 350 kg per meter cube we had assumed as the threshold to difference between the open cell and closed cell structure. So powers of 2 and 3. So here is your model. Of course, it was my model at one point of time, and you can see the meager amount of elements and nodes and degrees of freedom as compared to today's model. So this was way back in 1995 when I was doing my PhD in Delft. 1995 is a long time back, okay? So almost reaching 30 years in 2025. Okay, so it's a little less than that. So, of course, 25 years has gone by. Within that, the whole capability of computational resources have increased to such a great extent. Remember that time, it was a DOS version of ANSYS. And to run this model, I had to go to the computer center of Delft, having some supercomputer, and I had to run it through the night, at least five hours, to solve such a elementary level model as you can say it in today's world. You can just click of a button, you can solve it now on your laptop. So you see, the necessity is the mother of invention, as I understand it that way. So we did not have resource even in developed countries. So that actually triggers, alternative solution, more precise modeling without sacrificing the quality of the model in terms of discretization error. But here we came up with a shell solid modeling approach to reduce the number of elements. So you can see the fossa area, which is marked in purple, is basically the area which is very thin, and almost you can see through it. So you have the infraspinous fossa and the supraspinous fossa, which are modeled with shell elements. And you have the solid bony ridges, which are modeled with solid elements. But the cortical bone layer is modeled also with shell elements, in order to ensure that at the junction between fossa and the solid bony ridges, the connection is between shell to shell. Okay? Because shell elements had 6 degrees of freedom and solid elements had 3 degrees of freedom. Okay? So we had to ensure that there is no mismatch in degrees of freedom at the common nodes of the connection between the thin structures which have been modeled with shell and the thick structures which has been modeled with solids. Okay? So this is the first realistic model of the shoulder that came up, considering all the complexities, and you can see from the side view how complex is the model. It was so difficult to generate these models. And remember, it is based on CT scans. So the number of elements were about 11,000 only, nodes were 14,000, and total degrees of freedom was 63,000. So with all the muscles and physiological constraint condition, we had analyzed during abduction of the arms, it's 0 degree abduction, 30, 60, 90. So 90 degree abduction is the position where we have the maximum glenohumeral joint reaction force, which is about 400 newtons. Okay, 400 newtons means about 40 kgs, not very negligible. Okay, so we had actually quantified the stress distribution, and we could see that the thick bony ridges are the regions where there is a lot of huge load transfer happens, and the thin part, the fossa area, the stresses are very less. So this actually answers some important questions related with structure and function. Okay, so the thick bony ridges in the scapula are responsible for load transfer. Okay, whereas the thin bony parts act more as muscle attachment sites. Okay, so we had published this paper on load transfer and connected with the function, the structure and function. It does answer to the question, the important question: why is the structure of the scapula so complex, and what are the function of the individual parts, constituent parts of the bone? Like, for example, the scapular spine. You can see the scapular spine originating from the fossa and then branching out like a tree. Okay, but the spine is responsible for a high load transfer because there is a lot of important muscles, trapezius and deltoid, that take part during abduction, and there is quite an amount of bending within the spine as You can see there is bending within the spine, huge stresses, also in the lateral border. The lateral border is here. So both views, this is an oblique view, this is a posterior view. This is compressive stresses, mainly negative. So principal stresses are mostly compressive, and tensile stresses on the left-hand side. So you can easily see that there is a huge bending in the structure. This was the first model, first realistic model, so we had to undertake rigorous experimental validation. This picture was taken by myself, and this is a real bone taken out of donated cadaver bodies. Okay, remember, it looks like tandoori scapula, indeed, but it is real bone. Okay, and you can see that very thin strain gauges have been mounted, glued on different parts of the scapula. And the numbers that are written is my handwriting on the machine parts. 1, 2, 3, 4, and you have link mechanism to hold the scapula in position so that it executes. We had designed the whole mechanism in such a way during the testing that it behaves almost in a similar way as our shoulder does. Okay, so there is bending as well as direct stresses being induced in the different parts of the scapula, the normal stresses. So for different loading conditions, we had gathered data, and this was the best we could get when we have FE strains. Of course, the same model, we had to generate the FE model of the tested scapula, and we had actually FE strains prediction from the FE model, FE analysis, and measured strain is the direct measurement. So when you plot these two raw data, you can get hold of a relationship. And this was the degree of correlation coefficient. Correlation coefficient varied from about 0.89 to 0.97. Standard error was 29 to 100 microstrain. And percentage error in slope. So when we plotted, we tried to do linear regression analysis to find out the relationship between these two independent variables, measure strain and numerical FE predicted strain.
Various
okay. So this is a blowout
about the water jet machining.
This low region of stress between minus 250 to plus 250. So this part, okay, on both sides of zero, the first part, minus 250 to plus 250. Okay, I'm blowing up this and you get this. Of course, there is scatter. This is biological testing compared with FE predictions, but still you can see there is a correlation between these two. Therefore, an accurate, moderately sized FE model of the scapula was obtained using shell solid modeling approach and CT scan data. High stresses, tensile as well as compressive, were generated on either sides of lateral border, scapular spine, acromion, indicating bending of the structure. Okay. So the stresses were low in the fossa area, as you have seen in the picture, which indicate that the function of these areas is to act as attachment sites of large muscles, as I told you, rather than transfer of loads. Okay. So the FE model, along with the static shoulder model of forces, is useful for calculating stress distribution in various parts of the scapula during specific movements of the arm. Okay, so we had just given you some highlights of the results corresponding to abduction. Maybe other movements you can easily calculate when you can simulate the forces as applied loading conditions. The next comes is the implant. So we are evaluating implant with the bone and also at the material interfaces with regard to common failure scenarios for cemented as well as uncemented glenoid prosthesis. This is a nice picture which gives you a clear idea of what is happening inside the glenoid during surgery. Okay, so this is the total polyethylene component which is cemented like this. So the glenoid is sort of resected, and this is the keel. We call this keel. You see the keel? This is the total prosthesis. It can be total polyethylene prosthesis. It can be a metal back polyethylene component. Okay. Both are fixed to the bone with the help of bone cement layer. Okay. We have the cancellous bone, cortical bone. This gives you a clear idea of what is happening inside. And this is a FE representation of the prosthesis with the cement layer. So it is meshed. On the right hand side below is the uncemented prosthesis from Zimmer that we tried to model. It was an experimental design. So here you have a thicker metal backing with two fins on the superior inferior side and a hollow cylinder to hold it. Okay, so there are two fins which are offering more rigidity to the implant. It's basically a hemispherical type of implant, and you have a polyethylene component on top. But the amount of metal backing in this type of prosthesis, uncemented, is much more as compared to the cemented fixation. Okay. You actually allow bone to grow inside. You see, bone can be inside this hole. This is a hollow cylindrical component, which is an integral part of the metal backing, over which the fins are sort of attached. That forms basically the base or foundation of the prosthesis. Okay. So here we actually started. We applied the submodeling technique because we are now interested about more precise stress distribution around the domain of inclusion of the prosthesis. You can see already this prosthesis is sticking out, the blue one. So we have a submodel, and at this cut boundaries, we actually transferred the displacements from the overall model to the submodel. This is a very important slide for all of you. How are we calculating the interface stresses, and how are we concluding about interface debonding or interface failure? Okay. Now, I think if you are aware of Hoffman's, I'm not sure whether you are aware of Hoffman's failure criteria, which is mostly used for in composite material as well, the failure criteria, to evaluate or assess debonding of two materials. Okay, so are you there in the class? Hopefully you are.
Yes, sir.
Yeah. So I think Sebi is in the class. So composite materials. And how many MTech students have done the course on composite materials? I think Professor Atul Jain was teaching, right?
Yes.
Yes, sir.
Yeah. So, are you aware of Hoffman's failure criterion? The multi-axial, biaxial failure criterion? You have Shai Wu, you have Shai Hill.
Yes, sir.
But the origin is Hoffman's failure criterion. Okay. You can also search in the internet, you will get that. The origin, the genesis of these proposed Shai-Hill, Shai-Wu failure criteria is the Hoffman's failure criteria. Okay. So let me elaborate on that. It has been used quite effectively in assessing interface debonding at the different interfaces of the implant bone construction. Okay. Now, precisely if you look at the equation, first focus, let me focus on two terms, sigma n and tau. Sigma n and tau. Okay. These are normal and shear stresses at a point on the interface. Okay. Which can be easily calculated by stress transformation. Yes or no?
Yes, sir.
So at any point on the interface, you can, using the state of stress, you can transform the state of stress and find out at the interface the normal stress and the shear stress, of course, at a point on the interface. Now, this interface can actually change locations and change orientations. Okay, it may be vertical, the plane may be vertical, it may be inclined, because it depends on the how it traces the path. Okay, so at different points you will have a different set of sigma n and tau. Okay. Now, what are the other terms? Here it is also sigma n. What? ST, SC, and SS. These are basically strengths of the interface. Okay. So basically what boils down is the multi-axial state of stress versus the strength. That is what we actually do to assess failure. Okay. Now, how to get hold of the values of the individual tensile strength, shear strength, and compressive strength? Okay. Now, this has been worked upon, as I told you, between the implant and the bone, cancellous bone. The cancellous bone is always the weaker of the two, always the weaker of the two. So the strength of the local cancellous bone, strength of the local strength of the cancellous bone, or strength of the local cancellous bone, is of high importance. That will dictate whether or not that interface will fail or not. So, empirical relationships, as you can see, similar to modulus and density relationship, have evolved through testing as well as theory, and this was first proposed by Kaplan et al. And Stone et al. Long time back, 83, 85, and this has been proved to be quite acceptable. So you have the tensile strength calculated directly from the apparent density using the power law relationship, similar to the E modulus density relationship. Strength, local strength of the bone is also connected through power law relationships, okay, with the apparent density. So you can calculate the local tensile strength, compressive strength, and the shear strength of the bone, cancellous bone, using the value of the local apparent density, which you can get easily from the CT scan data. Okay. Now, if you put that value here in the equation, you will end up with a number. That number will be either less than 1 or greater than equal to 1. So anything less than 1, obviously physically you can understand the structure is secure and is less likely to fail. Anything greater than 1 is most likely to fail. Okay. Now this FL, a failure criteria of Hoffman, can be represented in, graphically as an ellipse in 2D as an ellipse, and in 3D as an ellipsoid. Okay, so what happens is not individual values of sigma n and tau, but a common combination the multi-axial state of stress as well as the local strength of the material. And it has been used very effectively to assess failure in an implanted structure. How? I will explain it now. Look at the results. So this is basically the stress, principal stress distribution in the cement volume, or the cement mantle as we call it. Okay, so one side you have total polyethylene, the other side you have metal backed polyethylene. It is similar to some extent, more or less, but you can see that the stresses are a little higher, more distributed in the total polyethylene processes, where it is little less distributed in case of metal backed polyethylene. But the high stresses in the cement mantle, this is, remember, this is principal stress, this is tensile stresses in the cement, bone cement, and cement has the inherent property of low tensile strength. Okay, so this can be quite threatening, and this can be one of the answers to the question that cement can fail near about the boundary of the implant bone interface. Okay, so cement failure, cement crack can be a potential cause of failure already, that is indicated from this stress analysis. If you look into the cross section, remember this is, we are plotting for 90-degree abduction of the arm. Earlier one also 90-degree abduction of the arm. Highest amount of forces during this glenohumeral joint reaction forces will always generate higher stresses. So if you look at the sectional plots, you have total polyethylene. You see how nicely the stresses are transferred from the prosthesis to the bone, and joining bone and finally to the cortical bone. Okay. If you induce a metal backing, a very thin metal backing of 1 millimeter or 1.5 millimeter, that is immediately sort of you see the difference. More stresses within the implant and less stresses in the adjoining bone. If you increase the metal backing, as in the case of uncemented prosthesis, no cement here, remember, you see how high are the stresses within the implant and less within the bone. Now comes a very important slide. I have to explain this slide. This is probably the last slide, but very important. Okay. Now the total polyethylene provides a more physiological stress distribution than the metal bag design. This is very clearly exhibited in the results. Now comes the evaluation of the cement bone interface, which has been indicated by clinical studies as a potential boundary of implant debonding from the bone, or interface debonding, interface failure. So adjacent to the tip of the keel, okay, let us go back to the figure. Adjacent to the tip of the keel, okay, here, you can see the keel is, I hope you have seen the keel. So this is the keel, which is going inside the bone. So adjacent to the tip of the keel is these areas, okay, these are these areas. adjacent to the tip of the keel appears very likely to fail. We had calculated the Hoffman's number to be 1.86 as compared to superior edges of the prosthesis. It comes out to be FL value of 0.19, although the stresses are not significantly lower around the superior edge. This is a very important conclusion. So you see that there is hardly any difference in the stress, sigma n and tau, but because the strength is lower around the central part of the glenoid, the bone strength, the local bone strength is lower, even at almost similar set of values for sigma n and tau, you see the difference in the FL value. So one comes out to be 1.86, the other superior edge comes out to be 0.19. So this is no way it can fail, but this is already high probability of failure. For metal bag design, the cement bone interface adjacent to the tip of the keel is more likely to fail because the FL values goes to 2.16 as compared to superior edge of the prosthesis, which comes out to be 0.68. Okay, so the implant cement interface stresses were higher for metal bag design. Obviously, this can be the only answer because if you compare the values, also it is evident that the metal bag design would produce higher implant cement interface. So this is evaluation of the cement bone interface, but in case of implant cement interface, you have for the metal bag design higher set of values as compared to the total polyethylene design. Now, there is some recommendation for the surgeons coming out of research. So, a part of the subchondral bone along the superior inferior direction of the glenoid, so top, bottom, along that, should be preserved in order to strengthen the glenoid. Okay, don't remove the bone, try to remove as less as possible, try to preserve the subchondral bone. What is subchondral bone? The subchondral bone is high density bone. So it is between cancellous and cortical. You can say more or less a compact type of structure, but it is high density. The more higher the density, the higher will be the strength offered by the bone, and thereby lesser chances of interface failure. Okay, the cancellous bone underlying uncemented prosthesis is subjected to lower stresses as compared to the cemented design, which might result in stress shielding. That already we have seen, observed in case of, as I presented the results in form of pictures or figures. But very important revelation comes when we play with the numbers. In case of the uncemented prosthesis, the implant bone, there is no cement here. The implant bone interface for the uncemented design appears less probable to fail. The highest FL value that came out for the implant bone interface in case of uncemented prosthesis is 0.84 as compared to cemented prosthesis, since higher interface bond strength is offered by the surrounding. Okay, so when you are replacing, carrying out the replacement surgery, shoulder replacement surgery, in case of the uncemented design, you are actually preserving more bone, more high density bone, and thereby the chances of failure of the implant bone interface is less as compared to the cemented prosthesis. Thank you. I hope you understood the essence of the story. Hello?
Yes, sir.
Because it is not, somebody can say high stresses, but the question is how high is the stress? Okay, well, no, it is not about just stresses. It is combined with the local strength that dictates failure. Okay, that is the main essence of the story. Okay, stress, say sigma n and tau, may come out as 10 MPa each, but that may not be sufficient to induce failure at a particular location because the strength might be higher. Okay, whereas 5 MPa can induce failure because the local strength may be lower. You get my point? Hello?
Yes, sir.
Yeah. Okay. So I hope it is clear. If you have any questions, go through this presentation and we can discuss it in the next class. But SEBI will come up with a friendly lecture more for your knowledge. And you, I think SEBI, you can take over quickly because we need to finish by 1.
Yes, sir. Actually, I have to create a new meeting because here I am not able to share the slide. Organizer. So I have actually created a new meeting, and it is scheduled for 12:30. I'm pretty sure that the meeting won't take more than 30 minutes. So if you want to take a break of 2-3 minutes, you can, because the meeting will start at 12:30. So 12:30.